Hello, welcome to 16.3 Bond Polarity. We will start off by doing a review of electronegativity, and this is the relative attraction that an atom has for the shared pair of electrons in a covalent bond. If you remember, we talked about this during the periodic trends lesson, and so it's basically in a covalent bond, one of the atoms typically has stronger electronegativity and will pull the pair of electrons closer to them. As an example, here we have hydrogen and chloride or chlorine. Hydrogen has an electronegativity of 2.1, chlorine has an electronegativity of 3.0. These electronegativity numbers can be found in your data booklet. They are found on a periodic table that also has like the, I think, ionic radius and electron affinity and things like that. But you can find this in your data booklet. So the one that's more electronegative is the chlorine. So that one will pull the electrons closer to itself. And that means that it has a slightly negative charge. We say that it is partially negative. And hydrogen here has a partially positive charge. This little symbol here is our partially symbol. So it's not like a full ion. It's not saying that the chlorine is for sure negative. It's saying it's partially negative, it's slightly negative, and this hydrogen is partially positive. This creates what we call a dipole moment. A dipole moment goes from the positive to the negative part of a covalent molecule. And we draw it like this, where we have an arrow pointing going towards the negative end, and this little line through the tail close to the positive end. Another example, here we have water, H2O. Hydrogen, like we said, has an electronegativity of 2.1. Oxygen has an electronegativity of 3.5. So that one is partially negative, and the hydrogens are partially positive. And we see here they actually have two dipole moments. And you would draw it like this, the positive end pointing towards the negative end. So make sure you can draw these electronegativity symbols on your and dipole moments when you are given a Lewis structure like this. In next year, you'll go a step further and talk about the polarity of entire molecules, but in this case, we just care about the polarity of bonds themselves. This leads into the types of bonds. So you can have a pure or non-polar covalent bond where the electrons are shared equally and there is no dipole moment, so there's no partial positive and no partial negative. Or you can have a polar covalent bond, polar covalent bond, where electrons are shared unequally, creating these dipole moments that we just talked about when the electronegativity is farther apart on the atoms you have. And then, of course, you can have ionic bond where electrons are transferred. To determine bond type, we have this triangle chart that will also be found in your data booklet that we can use to find out what type of bond is in each molecule that we are looking at. To do that, we look at the y-axis, which looks at the difference in electronegativity. So you take the electronegativity of the higher one minus the electronegativity of the lower one, and look where that puts you on the difference. Then the x-axis is the average electronegativity. So you add both of them together, and then you divide by 2 to find their average. Then you compare where it is on both sides, and wherever that point is, that is what type of bond it is. And those types of bonds are ionic, polar covalent, non-polar covalent, and metallic. So let's do some examples together. Predict whether the bond between sulfur and fluorine in sulfur tetrafluoride is nonpolar, polar, or covalent. And that should say ionic. That is a typo. I apologize. Is it nonpolar, polar, or ionic? So, sulfur has an electronegativity of 2.5. Fluorine has an electronegativity of 4.0. And each of the sulfur-fluorine bonds are exactly the same between all four fluorines. We look at the difference in electronegativity. That gives us 4.0 minus 2.5, which is 1.5. And then the average electronegativity, which gives us 3.25. So we pull up our triangle, our electronegativity triangle, which is in your data booklet. We look at the y-axis, should be about 1.5, which is here. And then we go to the x-axis, which is about 3.25, which should be about here, right? And that is very clearly polar covalent. So you would say it's a polar covalent bond. Another example, predict the bond between calcium and bromine in calcium bromide. Is it nonpolar, polar, or ionic? Well, calcium has a electronegativity of 1, and bromine has an electronegativity of 2.8. So the difference in electronegativity is 1.8, and the average electronegativity is 1.9. We look at our graph here. We go 1.8, which is about right here, and then 1.9, which is about here, and that is obviously in the ionic section. So we say that is an ionic bond. Last example, we look at oxygen gas. Is this nonpolar, polar, or covalent? Well, oxygen has an electronegativity of 3.5. 3.5 minus 3.5 is 0, and the average is 3.5. Looking at a graph, y-axis of 0, 3.5, we come right here, and that is very obviously nonpolar covalent. And that is how you look at the bond polarity. If a molecule had multiple different bonds, you should look at all of them separately to see what each of the bonds are by comparing the electronegativity of the atoms that they have. But that's how you do it. You use this graph that will be in your data booklet. And yeah, thank you guys so much for listening. I will see you next time.